This has been a wonderful journey, and this is a great chance for John to get to share it with all of you. So again, thank you for coming, and it's been a pleasure to work with you on this. So
it's been a pleasure to work.
Yeah, have a good time giving your presentation.
Thanks.
Yeah.
Hello, everyone. Thank you for coming this afternoon. The image before you is a photo taken from the west side of Horse Valley Creek in March of 1916 of the Horse Valley Creek Debris Control Dam, one of two debris control structures retaining hydraulic mining sediment in the Willow Creek watershed, the watershed where I focused my research. The title of my presentation today is Hydraulic Mining Sedimentation in the Willow Creek Watershed, Yuba County, California. This is my master's thesis defense. As you well know, my name is John Kelley. And I conducted this research under the supervision of Drs. Carrie Monahan, Dr. David Brown, and Dr. Bill Kushner. Just a brief overview. We go into a little background information, some of the methods I employed in my analysis, the objectives of my research, some of the results I found in my research, a little discussion on why I think those results turn out the way they do, and some recommendations for future work. This photo is of graduate student extraordinaire Sean Lucas scaling a cliff made of auriferous gravels in the Willow Creek watershed. And these are the gravels that the hydraulic miners were looking for to mine. Before we get started, I'd like to focus you guys on a question, the overarching question of my research. Can Dr. Alan James's method for locating and quantifying hydraulic mining sediment in the Bear River watershed be duplicated in the Willow Creek watershed? That's the first question I had to answer, and as we go into the talk, I'd like to focus you guys on that question from the start. So, backing up, during the late Jurassic and early Cretaceous, gold-rich quartz veins intruded the sediments overlying the Sierra Nevada batholith. During the Eocene, these sediments, and this right here is the Western Sierra Nevada metamorphic belt. During the Eocene, the entire area was uplifted, and the sediments, along with the gold-bearing quartz veins, eroded down, and those sediments were deposited in north-south trending paleo river channels. Subsequent tectonic events during the Oligocene and Miocene uplifted those Eocene paleo river channels. Just to give an explanation of this graph, right here are overlying sediments. AUB are the white gravels, the less rich but far more voluminous gravels that the gold miners were looking for. AUD are the blue gravels, the much richer but far less prevalent gravels. And modern stream channels then cut down through these paleo river channels to create the modern stream profiles we know today. As they cut down through these Eocene paleo channels, gold was deposited in the modern-day stream channels. When this gold was discovered in 1848, the California Gold Rush began. This image is the paleo river channels. The yellow is the paleo river channels as inferred by the miners. The blue lines named are all the current major river systems. You can see the Yuba right here. And the black dots, for the most part, we've got a couple of cities outlined, but the black dots, for the most part, are named hydraulic mining operations in this area. So, hydraulic mining. So early miners diverted these stream channels and just got all the easy gold out of the stream channels, but this period ended relatively quickly. So that by 1852, they were looking for the source of that gold, and they found it in those uplifted Eocene paleo channels above the stream channels. In 1852, the process of hydraulic mining was invented to mobilize that gold and extract it from those hillsides. Hydraulic mining works by creating a large reservoir of water upstream that pressurizes that water. The water is sent down through pipes into tapered nozzles and directed at the hillsides to mobilize the sediment in those hillsides, which can then be directed into sluice boxes, which are long rectangular trough-like boxes. And in those sluice boxes, the sediment and the gold is differentiated through gravity is separated through gravity differentiation. From 1852 to 1884, over a period of 32 years, 1.1 billion cubic yards of sediment was mobilized. This is a huge amount of sediment, and that sediment was allowed to flow downstream into the Central Valley, where it became a real problem for the farmers in that valley. This image was taken from G.K. Gilbert's 1917 seminal paper on hydraulic mining sedimentation in the Sierra Nevada. It's a picture of Marysville. The black dots over here are all hydraulic mining sedimentation. The levee is a 25-foot levee surrounding Marysville that still exists today, that was built to prevent the city of Marysville from getting buried again. It was buried in the flood of 1868. Once these sediment control measures were put in, Marysville was, for a time, safe, but it directed the sediment further downstream, so in the flood of 1874, Sacramento was buried. This greatly upset the farmers, and litigation soon followed. For about a decade, the judges went back and forth on who was responsible, and because they couldn't find a source, like a specific person to blame the sediment motion on, the judges didn't do anything about it, until 1884, when Judge Lorenzo Sawyer put an injunction on all hydraulic mining in the Sierra Nevada. This is a very unpopular decision, though, with the miners, so they lobbied the U.S. Congress, and in 1893, U.S. Congress passed the Caminetti Act, which allowed hydraulic mining to continue in the Sierra Nevadas so long as the hydraulic mining sediment never reached navigable waters. If you guys are familiar with the Clean Water Act, that phrase comes up quite a bit. Incidentally, the Sawyer decision is considered the first environmental law in the United States, so it's an interesting feature. The California Debris Commission was created to license hydraulic mines for operation and to make sure that they were all retaining their sediment. Over the 59 years of regulated hydraulic mining, 1,264 licenses were issued, and a volume of 31,916,000 cubic yards of sediment was licensed to be stored. If that sounds low compared to the 1.1 billion in the 32 years previous, it was. By this time, much of the easy gold had already been mined out, so many of these operations found the requirement to restrain their sediment too onerous to continue. One such debris control dam is the Willow Creek Debris Control Dam in the Willow Creek watershed. This dam is 80 feet tall, 100 feet across, 10 feet broad, and it restrains a hydraulic mining sediment deposit of a half-mile long and an estimated volume of 476,000 cubic yards. This dam is one of two that still exists in my watershed. So, very interesting history lesson, I'm sure, but why is it important to us today? This is a map of all the mercury, silver, and gold mines in the state of California. During hydraulic mining, mercury taken from the mines in the Coast Range was exported over to the Sierra Nevada to assist with the amalgamation of the fine gold particles taken out of the Eocene and Paleo channels. In a typical sluicing operation, 800 pounds of mercury would be seeded onto the sluice at the beginning of the season, and once a month an additional 100 pounds would be added to the sluice because mercury was leaving the system and not being recovered. During the period of unlicensed hydraulic mining, that 32-year period, it's estimated that 10 million pounds of mercury was lost. This mercury was lost into downstream waterways and ecosystems, where much of it still exists today. Mercury is a potent neurotoxin with the ability to cross the blood-brain barrier and the blood-placental barrier, and it has the ability to biomagnify up food chains. So people reliant on certain fish products are especially vulnerable to mercury toxicity. 75% of all the EPA fish warnings in the state of California are for mercury. So this is a continuous and ongoing health concern. And that mercury is still associated with these hydraulic mining sediments. So now, let's focus in on my research. This is the Sacramento River watershed. The city of Sacramento is highlighted by the red star over here. A subwatershed of the Sacramento is the Yuba River watershed. A subwatershed of the Yuba River watershed is the northern Yuba River watershed. And a subwatershed of the northern Yuba River watershed is the Willow Creek watershed, where I focus my research. This is a LiDAR image of the Willow Creek watershed. The three named creeks where I focus my sampling are Brandy Creek, Horse Valley Creek, and Willow Creek. There are 6 large named hydraulic mines in this watershed. The watershed itself is about 8.6 square miles. And this watershed was in production from 1852, when gold was discovered, to 1941, when the last CDC license was revoked from Depot Hill down here. Just to give an idea of the production of this watershed, from 1860 to 1874, $8 million worth of gold was pulled out of this watershed. In today's money, that's $206 million from 8.6 square miles. The 2 debris control dams in the watershed, the Horse Valley Creek debris control dam and the Willow Creek debris control dam, are highlighted by the red dots. A LiDAR image is really nice to identify hydraulic mining features because they really stand out. If I hadn't highlighted them with these black lines, it'd still be easy to see these large exhumed pits on this digital elevation model. And these are not the only hydraulic mining features in this watershed, those are just the largest features. And for reference, here's New Village Bar Reservoir right down here. Hydraulic mining sediment is also creating a problem for reservoir capacity because this stuff is still moving downstream and decreasing the projected life of these reservoirs. So, just another thing to keep in mind. Now, what did I do? The photo before you was taken by Dr. Alan James at the University of South Carolina of the high terraces on either side of the Bear River. When Dr. James was doing his PhD dissertation at UC Davis, he was looking for a way to quantify the percent of a sediment deposit that was directly related to hydraulic mining. He realized that if you could come up with 2 end members, the percent white quartz in a watershed if no hydraulic mining had occurred there, and the percent white quartz of pure hydraulic mining sediment in that watershed, he could create a sediment mixing ratio relation and then use that relation to determine what percentage of sediment deposits are directly derived from hydraulic mining sediment. He started with the high terraces in the Bear River watershed because during the period of peak unregulated hydraulic mining, there would not be a river channel here. From here over to the opposite bank would be pure, undiluted hydraulic mining sediment coming out of the large mines. It would periodically move downstream during large water years, during the floods, to flood those downstream communities. But all of this sediment, these high terraces, are pure hydraulic mining sediment from the period of unregulated hydraulic mining. The river channel just cut straight through them because they were unconsolidated gravel deposits. Nothing to hold them together. So that's where he got his 100% hydraulic mining sediment, end member. And then going above where any mining had occurred in the Bear River watershed, he found his white quartz percentage of sediment free from the influence of hydraulic mining. These are the two end members of his sediment mixing ratio relation. Now, this is what the equation looks like. I'd like to take a moment here to really explain this so everybody understands what I did. The percent MS, the sediment mixing ratio, which is the percent of a deposit that is directly derived from historical hydraulic mining, equals the percent white quartz in that particular sediment sample minus the other alluvium end member, the percent hydraulic mining sediment you would see in a deposit free from the influence of hydraulic mining, times 100%, over percent QT, the mine tailings end member, 100% hydraulic mining sediment, minus the other alluvium end member. Dr. James focused on the white quartz gravels, so he focused on the percents, the size range from 6 millimeters to 64 millimeters, and the percentage of a deposit, the white quartz percentage of a deposit in that size range was used to get your sediment mixing ratio. That size range will become important later in this talk. So this is what I did. Before I could start using the sediment mixing ratio, I had to come up with these two end members. I had to find them in my watershed. But once again, this is a LiDAR image of the Willow Creek watershed. For reference, the two debris control dams, Horse Valley Creek and Willow Creek, are over here. New Bullard's Bar is down here. And so the first thing I did was I had to find an area free from the influence of hydraulic mining in this watershed. Not an easy proposition in this watershed because so much hydraulic mining occurred there. But if you look upstream on Horse Valley Creek, none of the usual hydraulic mining features appear. This was confirmed with field reconnaissance, and 7 samples of the other alluvium end member were taken up here. Next, I went to the high terraces on either side of Willow Creek and Brandy Creek and sampled them for my mine tailings, 100% hydraulic mining sediment end member. Using these two end members, I could then construct a sediment mixing ratio relation. And just to show that the two populations, other alluvium and mine tailings, are different, here's a bar graph. Down at the bottom is the percent white quartz. Over on the y-axis is the number of samples. And I found, for the Willow Creek watershed, the mean white quartz percent in the other alluvium sampling population was 2.86. The mean white quartz percent of the mine tailings population was 50.33, n equals 7 and n equals 2 respectively. Just as comparison, here's a recreation of Dr. James's data from the Bear River watershed. Down the bottom, once again, is percent of white quartz, number of samples over on the y-axis. And he found in the Bear River watershed a mean of 2.6 and a mean of 56.6 respectively. The two graphs are very similar, our numbers were very similar, and they're both in the western Sierra Nevada metamorphic belt and underwent similar processes. So this gives me confidence that my sediment mixing ratio, which I've constructed for the Willow Creek watershed, is viable. So, moving forward, now that I have my relation, 80 individual sampling locations were sampled for 91 individual samples, all throughout the Willow Creek watershed. When sampling, I filled up a 5-gallon bucket with sample, washed away everything less than 6 millimeters, took a random assortment of those pebbles, spread them out over an alphanumeric grid, and counted until I had counted 100 pebbles, and therein determined the white quartz percentage in that sediment sample. Of these 91 samples, I divided them into six populations based on their location and geomorphological signature. The 6 populations are shown right here. Their respective sediment mixing ratios are over on the y-axis. The population name is over on the x-axis. And from left to right, first are 2 end members, other alluvium, and mine tailings, n equals 7 and n equals 12. Then over in Joubert Diggins up to the northeast of the watershed, I sampled the in situ auriferous gravels that you saw Sean Lucas crawling around on in the very beginning of the talk. I sampled the sediment deposits behind the Horse Valley Creek and Willow Creek debris control dams to see what they were like. And then I sampled lower terraces, those terraces less than 6 feet outside of the active channel, and gravel bars within the active channel. These two I consider active channel samples because they can be affected and mixed by modern day hydrological events. Now, with these 6 sampling populations and the samples, I can start to make inferences as to the movement of hydraulic mining sediment in this watershed. So now, my objectives. First, and don't worry about reading it, you're going to see this slide a bunch. Do the sediment mixing ratios of samples taken along the riparian corridors of the Willow Creek watershed show longitudinal trends related to the movement of historical hydraulic mining sediment in the watershed? The first riparian corridor I looked at was Willow Creek itself. 9 samples were taken along, 9 active channel samples were taken along Willow Creek from upstream to downstream. The 2 debris control dams are the little dam locks on the map, and New Bullards Bar Reservoir is down here. And the relative size of the circles shows the relative sediment mixing ratios seen along the riparian corridor. Joubert Diggins is also included to give a reference for what an in situ auriferous gravel would look like, because that is the sediment, that's the inferred sediment source for these samples along the Willow Creek watershed. And when these sediment samples were examined, 2 populations were seen. A population above the Willow Creek debris control dam with relatively higher sediment mixing ratios, and a population below the debris control dam. Down here on the x-axis, from 0 to about 8,000 meters, goes from the initial sample at Joubert Diggin to a final sample near New Bullards Barn. And over here on the y-axis is the sediment mixing ratios of those samples. The 2 populations were broken up. The 2 populations were examined and were found to be statistically different. Just a note on statistics before we move on. All of my statistical analysis was done using the programming language of R. All of the tests I'm going to be presenting today were done using non-parametric tests because normality could not be assumed with a sample size this low. And for the purposes of this study, a p-value of 0.1 was considered significant. And as you can see, the above population is significantly different than the below population. The sediment mixing ratios are over here on the side. N equals 5 and N equals 4 respectively, with a p-value of 0.06. Thanks for attending. Next, let's look at Brandy Creek, the westernmost creek that I looked at in my study. Once again, the relative sediment mixing ratios of the samples is shown by the relative size of the circles. And the Horse Valley Creek debris control dam is right here for a spatial reference. And once again, I found 2 distinct populations, but this time, rather than being larger upstream to larger upstream, it was actually smaller sediment mixing ratios in the upstream, and then larger sediment mixing ratios in the downstream. This is not the break I have put at Youngs Hill Road, but Youngs Hill Road is not the impediment. So It was just an easy geographical marker to show above and below. Here are the sediment mixing ratios of those samples from the initial sample taken on Brandy Creek to the final sample taken near New Bullard's Bar. The sediment mixing ratios are over on the y-axis. The x-axis is the distance from initial sample. And as you can see, above Young's Hill Road has a significantly different sediment mixing ratios than those taken below Young's Hill Road. Once again, sediment mixing ratio on the y-axis and the two populations are on the x-axis. The statistical significance of p equals 0.02. The last riparian corridor I looked at in my study was far shorter than any of the others. It was from the tunnel outlet at the north cut of Weeds Point Mine to its intersection with Horse Valley Creek. I wanted to see what would happen if in a direct source to sink sediment relation, and I found that from source to sink, the average sediment mixing ratio, the sediment mixing ratios of my samples had a general downward trend. Sediment mixing ratios are over here on the y-axis, and the distance from the mine outlet is over here on the x-axis. So, next, I want to see how do the sediment mixing ratios of the three laterally connected sampling populations, mine tailings, lower terrace, and gravel bar samples, compare with each other in the Willow Creek watershed. Now, what do I mean by laterally connected? Laterally connected, I mean if I start on one high terrace, move down to the lower terrace, across the gravel bar, up the high terrace, and up to the low terrace and up to the adjacent high terrace, they're all laterally connected across the stream channel. Okay? So, the mine tailings samples are up here, which I took from the high terraces in the Willow Creek watershed. Low terrace and gravel bar samples are both active channel samples because they can both be affected by modern erosional, depositional, and mixing events, whereas the high terraces, so far removed from the active channel, only erode. So this doesn't mix. And when I look at the three populations, I see a distinct downward trend from mine tailings to lower terrace to gravel bar. The sediment mixing ratios of my samples are over here on the left, and that's what I found. Finally, I want to see if there is a difference in the sediment mixing ratio of samples collected from the first foot, the 0 to 1 foot depth, as compared with the second foot, the 1 to 2 foot depths, in samples taken from the deposits behind the two debris control dams in the Willow Creek watershed. I did this by digging sampling pits along the top of the deposit. And when I asked this question, I did not find a difference in the sediment mixing ratios, a statistically significant difference in the sediment mixing ratios of the 0 to 1 and 1 to 2 foot populations. Sediment mixing ratios are over on the left side, and P equals 0.19 for this test. So, no difference. Now let's talk about why. Why did I see the things? Why do I believe I saw the sediment mixing ratios drop from upstream to downstream along the Willow Creek riparian corridor? Well, one possible explanation would be the debris control dam. All of the sediment sources, all of the hydraulic mining sediment sources along Willow Creek are above the Willow Creek debris control dam. There's Joubert Diggins up here, the south cut of Weeds Point Mine right here, for which the dam was originally built. And down here below the dam, there's a distinct dip in the sediment mixing ratios of samples taken therein. Remember, I only looked at gravels of 6 to 64 millimeter range. This is generally considered bed load, in a watershed of this size. So gravels of this size would not be able to leap over the dam unless some extreme hydrological event. So this is a possible explanation for the lowered sediment mixing ratios along this riparian corridor. Next, Brandy. So in Brandy, you have the opposite situation. Lower sediment mixing ratios in the upstream and higher sediment mixing ratios in the downstream population. The difference between Brandy Creek and Willow Creek is the location of the sediment sources. So in 2017, Dr. Gail Bacher and 2 field assistants went out and examined the hydraulic mining features in the Willow Creek watershed. And during that process, she found there was sediment movement and water movement out of these 3 mine outlets from Galena Hill Mine right here, and these 2 mine outlets from Young's Hill Mine over here. There are mine outlets down here in the Willow Creek, but no evidence of sediment movement or water movement was seen in those mine outlets. So the sediment sources for Brandy Creek are downstream of Young's Hill Road. There aren't really significant sediment sources upstream. So lower sediment mixing ratios in the upstream population than the downstream population. So Young's Hill Road is that guy right there. Next, about the deposit. Why didn't I see a statistically significant difference in the sediment mixing ratios of the 0 to 1 and 1 to 2 foot range? I postulated there would be a difference between the two because I thought there would be I postulated there'd be a difference, and there was, but it could not be captured using my analysis. This is a picture taken of the side of a creek, creek side of Willow Creek, running over the debris control dam. I did see 2 distinct layers, a hydraulic mining layer beneath a surface layer, but there wasn't that dividing line could be at any depth. There were some sampling pits where it was hydraulic mining layer at the surface. There were some sampling pits where I never hit the hydraulic mining layer. Because I washed away everything below 6 millimeters, this surface layer, which is mostly fine muds, sands, and silts, was completely washed away. This analysis does not capture this, but this is what I found in the field. So this is a different method should be used to analyze these sediment deposits contained behind the debris control dams. That was my work. I'd like to make some recommendations for future work that can be done in this area. First, and to me most importantly, this was a very interesting project for me. I had a lot of fun doing it, but what is the power of it? If a relation can be created between the sediment mixing ratio in a watershed and the extent of mercury contamination in a deposit of hydraulic mining sediment, you would have an easy mineralogical tracer for mercury contamination of a sediment deposit. This would be huge. This could direct stakeholders towards their remediation efforts. It could focus contamination testing. This, to me, is the power of this research, and I think the next step that should be taken to make this research relevant to the larger scientific community. Next. So I only looked at the gravels, but there are finds all throughout this entire watershed which has been affected by mercury. If you go to the debris control dam during a winter storm, the water running over it is a nice chocolatey red. It's very, very distinct color. So I would recommend analyzing the mercury content of the fine particles, the less than 0.063 millimeters, those most likely for the very fine mercury particles to adsorb onto, which are running over the debris control dams and out of the mine pits to determine suspended load contamination levels. So how much mercury is actually leaving the system where a lot of mercury was used. And next, personally, I would like to see what the sediment profile from top to bottom of the sediment deposits from the Willow Creek, from the debris sediment deposits behind the debris control dams is, to see if we can tell we can relate that sediment core to the history of hydraulic mining, because it started and stopped over the entire course of the period of hydraulic mining was going on in this watershed. So we may be able to, one, see how much mercury we could take out of that core, and two, just see if we can relate the history of that hydraulic mining to the sediment core we pull out of the sediment deposit. That's of great interest to me. So, before I end, I'd like to acknowledge some of the people who helped me here. First, Dr. Kelley, my advisor, for all of her assistance and patience. Next, Drs. David Brown and Dr. Bill Christner, for all of your patience and for helping me with those references, Dr. Brown. The Geos Department at Chico State for being so welcoming to me when I got here and for all the assistance you guys have provided. And my friends, research assistants, and Sherpas who would continuously come out with me into the field thinking we were going to have a nice day in the woods and ended up hauling several 100 pounds of gravel back to the car up hills. Here's a list of some of the references. I selected references for this talk, and that's it. Thanks, guys.
Any questions?
Any questions? Shoot.
I have one. Looking at the Willow Creek watershed data, I noticed you had far up in the watershed, it seemed like your hydraulic mining sediment mixing ratio was slightly lower than what you're finding further down.
Yes. Yeah.
Can you explain that?
I can definitely explain that. Actually, that was a research question in the thesis that I chose not to go into in the talk. What you're looking at here were right here.
Mm-hmm.
These are sediment samples taken from the pit walls of Joubert diggings. Those are in situ auriferous gravels. Those are the gravels that the hydraulic miners would have mined if they had been allowed to continue this process over and over. So these haven't been hydraulic mined. They're just taken straight from the pit wall. What that means is they did not undergo the process of hydraulic mining, which is a destructive process. So I'm looking at white quartz pebbles, a relatively resistant sediment clast. There are other sediment clasts in there that would be broken up by the process of hydraulic mining, like less resistant metasedimentary rocks. It wasn't just water they used; they also used dynamite to kind of, like, they shove it in there and blast the entire thing out and then wash it down into the sluice. So the process of hydraulic mining itself would increase the sediment mixing ratio of hydraulic mining sediment as compared with the original in situ auriferous gravels.
It would increase it downstream.
Yes.
Okay.
Yeah. Did that answer your question?
Yep.
Other questions?
I've already seen it so many times.
Good friend.
Yeah.
Nobody? Yeah, you can help me out. Nobody has to ask anything. You just come up and get stuff and leave. Yeah, no, it's free.
All right. Good
Guys.
job, John.
Sweet.